CLI and a cross-platform IDE for C and C++. Download now.
Hello, welcome everybody to my talk. My name is John Lakos. I work at Bloomberg in the office of the CTO, and I have a few layers of slides here. And the first one is the Bloomberg slide, and then the next one is my own slide, and that's was changed just because I forgot to update it. I've been working on this for the past week, and then for the past month before that, and then for about the past 7 months before that, in increasing levels of urgency. It turns out that a lot has been happening recently, so I couldn't really have written this slideshow 6 months ago. So this is kind of new and interesting information. I'm new at it, some of it, and I'm quite old at other parts, and I'll give you a little history of what's going on. This is the abstract, but since you're here, you don't need to read this. You already know what this is. I put it here for people who are going to be seeing it on the video. So I'm going to proceed to get into this. The motivation is I would like to help C++ survive long after I'm no longer here. And the way that we want to do that is to address certain issues that have come up, and we're going to talk about those. And of course, one of the big ones, which is the title of the talk, is safety, but there's a little bit more to it. I'm going to try to focus on the safety aspect. So depending on what the timing is, I might brush over some of the other things, but at least it'll be on the slides and it's something that you could go back and look at. As I said, I haven't given this talk before. It's brand new. It's interesting. I hope it gets across what I wanted to do, but this will certainly give me an opportunity to find out how I can do better the next time. So there are a number of people who are concerned with what's going on, and I'm just going to list them out here without repeating it. But there are various different organizations and groups that are saying that C++ isn't the safest language to write in. I think we all know that. The major companies that have been using it are backing away from it. And Google, for example, is a classic example where they pretty much just said, no, we're done. And Microsoft is not quite so brazenly, but is looking to other safer languages. And Adobe very quietly regrets that it needs to do something because the way C++ is right now, it's untenable for anybody but pretty senior people to get multi-threading right and so on and so forth. So the goal here is to reinvigorate C++. And what do we mean by that? Well, there are three aspects to C++ that need some attention. We need to make sure that it's safe, and we'll talk about what that means. We need to make sure that it's healthy, the environment is healthy, and we need to make sure that it doesn't lose its efficiency, which is its competitive edge over many other very powerful languages. So three primary areas of focus, correctness, and security. And these are just broad subcategories. Then health, the ecosystem, right? We need to make sure that our compilers are working, and efficiency. We need to make sure that all of these things maintain their potency because C++ is a very efficient language if done properly. And we want human efficiency. We want to make sure that people who are using C++ aren't taking forever to get done what they need to do. So making it safer. So correctness, essential behavior is as intended, detecting defects, making it secure, which is, it's not easy for people to exploit defects, and internally resistant to malicious attack. Okay, so making it healthier, the ecosystem, compilers, libraries, and supporting tools, etc., standard library, sanitizers, testing frameworks, fuzzers. So that's an example of the kind of thing we might want to do in the ecosystem. Efficiency. So there's machine efficiency, which is making it faster, executables and such. And then there's human efficiency, which is developing, making sure that developers' efficiency is maximized. So these are different aspects of that. What do we aim to achieve? So these are some things that we want to achieve: making it easier to use, closing the gap with other safe languages, blunting the desire to move to another language, especially if you're a power user of C++, like Bloomberg is. We've been using C and C++ for many, many, many years. and we've established quite a powerful code base. And every company will tell you, Google, Microsoft, Adobe, and anyone else, that with their huge code base, they are not going to rewrite it. There's no return on investment of doing that. They will need to maintain it indefinitely. So while they might move new projects to other languages, they're still going to need to maintain the C++. Bloomberg's been around since the 1980s, so you can imagine that we have quite a collection of very interesting C and C++ that we would not want to try to rewrite in another language, especially since it's been burned in and we know it works. So we want to improve the typical user's experience, of course, that's another thing, and set an example for other organizations. Hint, hint, wink, wink. We want to partner with other people. Anybody who's interested in helping us do what we're doing, we love to hear from you. And I'll remind you again at the end. So other organizations, please. And we're not talking about fixing something in 3 months. This is not a 3-month effort. This is a very long-term effort, and I want to illustrate how long-term it is. So I spent literally days writing a few slides to show you just how long-term it is. So this is Timur's slide, and I just want to mention quickly, because I don't want to go over this too much. How many people were at Timur's talk, by the way? Excellent. So I'm going to sort of gloss over some of the stuff that he talked about, and I'm going to get into some of the other things. I'm just going to mention contracts because they are important, because that's one of the things we know something about. So this is Timur's slide, and this was the first attempt when it started, and this was and it ended, and I wasn't even aware of it at the time because I wasn't part of the standards committee. But this was my attempt with another fellow in my group, and it died quickly because it was macro-based. Then we started another one, and with Nathan Myers came up with something which was really reinvigorated this whole thing, which was we would not only get runtime checking, but also compile time analysis. And he added, thirdly, that we could identify things that specifically could be assumed. And he did it with the current language without any new features, kind of like the way Andrei Andreescu created an entirely different paradigm back in 2001. Nathan created a paradigm, and we call it the assumed semantic. And people are scared of that. We're not going to worry about that right now, but it's something that will come up and will be fun to deal with in the next session of the standards committee. But anyway, we worked on that, and with Strustrup and others, and at the last minute, it kind of got yanked from C++20. It was in there for a year, and then we realized that there were some fatal flaws, and they were really. It's not about the general design. Contracts are actually very easy, but there are some little subtle things that when they interact with the standard that make it a little difficult. So won't go into that, but it died there. And right afterwards, we started the next generation and got voted in February. And basically, you're here. Now, what I wanted to do is just mention a couple of things that went on behind the scenes that I don't think Timur mentioned in his talk. First of all, I started this stuff in 2003. So that's where I come in. And it was in use at Bloomberg shortly thereafter. And then I gave it a little bit of a facelift and put in a lot more usage examples and pretty much productized it. And then we open sourced it. This is a very important one, the one in purple. It was at this point that we realized we'd been using it for a very long time on new code. But when we started to introduce it into older code, we had a huge problem. And the huge problem is, if you introduce a contract check into existing working code, and that code is wrong, what do you do? It will break the working code, even though the code is wrong. So it's one thing to put a contract check in new code, because if the new code is wrong, nobody's using it, it will break in your hands, and that's good. But if you've got something that's been running for 10 years and it's working, and you put a contract check in and that contract check aborts the way CAssert does, you literally cannot put it in. So we had a conundrum. What are we going to do? So next thing happened is we got Josh to come and join Bloomberg. And the very first thing I asked him to do was, please write an entirely new facility that parallels the current facility. The only thing that it does differently is it doesn't abort. It just continues. What? You have a bug and it just continues? Yes, because we'd like to know that we have a bug. So at some point in the near future, we fix it without crashing the entire system. What a good idea. So that was new. And then we wrote many papers, and there was much reflector traffic, and I mean much. And then we started sponsoring 20x features and contracts MVP advocated by Timur Dummler. And then Bloomberg sponsors MBV, Clang, and GCC. And these are the people involved. And then Bloomberg arranges for recorded safety panel, which was hosted by Phil, and that went very nicely. And against all odds, it got in. And then this is from our CTO, and he authorized this, so I'm very proud to say it. So Bloomberg continues to support prototyping and productizing the C++ 26 contracts MVP and beyond in Clang and GCC. This is Sean Edwards, my boss's boss's boss. This is good news. So the message here is Bloomberg is supporting this effort, and it's spending a ridiculously generous amount of money to help. We're trying to help. And again, I'm encouraging anybody who's interested in helping us, you know where to find me. So just to tell you what goes on, how the sausage is made, I spent quite a bit of time trying to figure out how to do this. So here's what happens. We have some critical thinking. It goes along here in the proposals. That failed. Okay, we try again. And critical thinking and makes it into compiler prototypes and the language, or excuse me, into the language. And then we start doing some prototyping because it's in the language. We need to make it happen. It's not really a prototype. It's more like implementing it. And we were implementing it. And unfortunately, it got taken out, which means we stopped doing those proposals. But there was still some benefit because we started again. And now we fed back what we'd learned from the original prototype. And that started some more prototypes. And then that continued. And then eventually we got it back into the language. And then we project that it'll stay in the language. We're optimistic this time. And then at some point, the compiler people will catch up and have all of the stuff that was in C++ in the trunk release, or as much of it as they can. And then here we are, we have it in trunk. And then at some point, much later, the company, whichever company it is, will finally move to this new release. Now you might think, why does it take 4 years? Because the larger the company, the more stuff you need to do to make sure that the new release, which is never easy, actually doesn't break anything. So 4 years is not an unreasonable amount of time for a very large company. It's not good, but it's not crazy. Now, finally, it's in production. So let's take a look at this. That's the starting point. That's the ending point. This took 5 years. That was a long time. This took 1 year. This is expected about 4 years. So you get 10 years. That's a long investment, right? We could do better. So instead, oh, by the way, this is the projected progress that we plan to make. Let's look at what we would do if we did it a little bit better. So we get an idea and we do this work. This is good. And then it comes down and gets in the language, and that's nice. And then a year later, we do this, and that's nice. And so here what we're saying is instead of taking 2 C++ cycles, we took just 1. So 2 years instead of 5, 1 year, still 1 year, and 4 years. Can we do better? So the theory is we can compress this a little bit more like this. Ideal. When we get to this point and it's in the trunk, we take the prototype that's already been written because we did the work and we start developing against that. And in theory, if we really start to catch up, we might be able to anticipate the fixes that we need in production so that when this finally drops, we just go. So in theory, you could imagine that a compiler release could happen in April of 2026, that the standard could come out in the fall of 26, let's say, and as soon as the standard is out, we could move to production next week. So this is ideal. Anyway, I'm just trying to get across to people that this is not something that happens overnight or in 3 months or in 6 months or in 12 months. But we all plan to live another 4 years, and we really will want this in 4 years. So it's just like saving money. We want to make it happen. And now we get 3 years. So this is the goal. This is idealistic, probably not going to happen, but we can aim for it. All right. What does safe mean? Different things to different people. It's secure and well-defined. Surprisingly, correct behavior is not something people talk about a whole lot, which blows my mind, because if you have correct behavior, these other things take care of themselves, pretty much. In any event, does what it's intended to do. So as I said, surprisingly, this is not part of safety. Who knows? Memory safety. Anybody want to take a shot at a one-sentence definition of memory safety? Anybody? Feel brave? All right, I'm going to throw this out. Language is memory safe if it does not permit access to unallocated or uninitialized memory. Do you believe me? Or does it mean something in addition to that? A lot of people say memory safety is good code. It's like, if it's memory safe, it's good. That's not entirely true. Memory safe is very good to have, but it doesn't cover everything. Can anybody think of something that is undefined behavior that isn't a memory safety violation? Yes, integer overflow. Excellent. That's the example. So integer overflow, right? Garbage collected languages do this. Java, Python, JavaScript. Functional languages. I have never programmed in a functional language, I don't think, except Lisp. I'm sad to say. Languages that enforce the law of exclusivity. What does that mean? Well, Rust and Swift 6.0 do this in different ways. Basically, one or more readers or just one writer. That's the ultra short mnemonic of what we're talking about. It's basically avoiding race conditions. And you get a lot more out of it from that. But anyway, so I could be a little more precise here. We can allow write-only access to uninitialized allocated memory. All right. What memory safety isn't? Right? There's undefined behavior that exists. And here's an example that was mentioned by this gentleman. Thank you very much. Where this code would exhibit undefined behavior. In fact, it must. It's in main. And you see what's going on? And yet, we can write that code and it will do something, right? It'll do something. It just isn't clear what it would do. Now, there was a talk that I went to a couple of days ago on dangerous undefined behavior, or dangerous optimizations, I'm sorry. And this was an example. And this can do lots of things. And there's typical things that it could do, but we don't care. We're not interested in that kind of gambling. So this is not a violation of memory safety per se, but it's not good. So we have to address this as well. So what are we trying to achieve? Security and correctness. This is what we're trying to achieve in the safety aspect. And by security, if we could simply recompile our code so that we get rid of all of the kinds of behavior that would cause a security problem, that would be amazing. So it turns out that there are two kinds of things we can do. We can fix the undefined behavior in the language, in the core language itself, such that you can't do anything there. That's amazing. And we can do that without having to rewrite any code. We could do that today. Correctness. This one requires that we go into our library code and do the same thing with the source code. And that's a lot of work. So those who choose to do that That's great. However, if we do that for the implementations of the standard library, you get a huge chunk of that too, because anybody who calls into the standard library will now be told, you're calling me out of contract. If they want to be told. And if they want to be told, they can also choose what happens. Does it terminate the program? Does it give you a message and continue? The nice thing about contracts is it must be all things to all people. Otherwise, somebody will complain. And it is all things to all people. The best we can do. And as I said, we've been using this model at Bloomberg for now, it's 2025. We started at 03, so that's 22 years. Really 22 years of experience. We don't have a problem with the model. It's all about the nitpicking of the standards committee to get it just right. But a macro-based model works really well. So that said, tools that address UB and C++. So there's no one tool. What do I mean by tools? So runtime contract checking is a tool. Erroneous behavior is a tool. Symbolic contract assertions is a tool. Does anybody know what I mean by symbolic contract assertions? It's basically stating something that can't be checked, but it's true, and it's in the interface. Profiles. Boy, is that a sore topic. And compile time enforced exclusivity. What's that? That's what Rust and Swift do. No, excuse me, that's what Rust does. And 6 is Swift, and it has a much more runtime enforced exclusivity. I am not aware of how Swift works exactly, but I have been told by people like Sean Baxter, who I truly trust, since he did the Rustification of C++, or making C++ compile time safe using exclusivity, that's 5, that Swift is very similar. And I've been told by other people, such as Mongo and Josh, that Swift is much closer to a runtime approach than 5. Again, I'm a little out of my depth there because I'm talking about some very specific things that I understand, and I have not worked with Swift, so cannot speak to that. All right, runtime contract checking. This was in Timur's talk, so I'm not going to spend a lot of time here. I'm just going to go through it. There's a plain language contract, a natural language description of what's going on, and then there's a contract assertion, which is C++ code. Make sense? We know that. Okay. C++ 26 contracts MVP features. Oh, I said that. Okay. So preconditions and postconditions, that's important. There's a standard way to get the violation handler. There are 4 standard semantics. Here they are. And there's a 5th one, which I alluded to, assume. It's not in the standard yet, but we all know it exists because if you call a standard library function out of contract, it's core language undefined behavior according to the standard. Now, whether people do something about that or not, that is what the assume semantic is. It's stating that if you call this out of contract, compiler can do whatever it wants to do. So don't do it. But you don't have to use the assume semantic if you don't want to. You can use any semantic you want. And then once your program has been sitting around for 20 years and it's never had a bug, you can turn your hard checking into ignore and then assume. And the code should just continue to work because contracts don't affect correct programs at all. That's very important to understand. If you have a contract that affects the essential behavior of a program, you have a bug. So simple use case. You could write something like this, by the way. This is pretty precise. This really gets you the result you want. But this is a lot of work. But people who write standards code can do this because they know what that all means. I actually did this. It actually works. It's pretty cool. But we use the parameter in the post condition, and it turns out that this is one of the problems of C++ because we want the efficiency. We don't want to make copies. And at the same time, we want to be able to use the parameter at the end. So if the parameter changes, that's a problem. So it turns out we have to do this. And I know that looks really ugly. Believe me, I hate it. But by doing this, we're basically telling the compiler for reals that we're not going to change X, and therefore this is all okay. So that's what we do for post conditions. If you don't like to do that, either don't use post conditions, or if you use post conditions, don't just don't name the parameter or something you want to look at. And if you do, then you just have to make it const. And guess what? We have a feature coming in 29 that gets around this. So it's just 3 years away. So most important usage. Here we want to make sure that the bracket operator doesn't get used in a bad way. We don't violate the contract. If we did this, we would be amazingly ahead of the game, because this is where most of the errors occur, when you call something out of bounds. This is the big one. This is like, we all talk about all kinds of bugs that can happen, but this bug is the bug to be scared of. All right. So that's an estimate. It's not just our estimate, but it's also, we internally have this estimate, but other company or other statistics have come up around 2/3 as well. Now, we sometimes call this code ghost code. Why do we do that? Does anybody have an idea why we call it ghost code?
Depending on the contract enforcement, it may or may not be generated and executed in the application.
That is exactly correct. So thank you. So we don't know if it's there. Since we don't know if it's there, we can't depend on it. So one of the important ideas about the architecture of building contracts is that you don't depend or think about, as the caller of the thing, whether it has a contract or not, or what mode it's in. As soon as you start to do that, you've fallen off the road and you're in the weeds. So you need to remember, don't do that. So that's why we call it ghost code, because it might not be there. You don't know. Teaching is easy. A contract assertion predicate should have no side effects. Tell all the people, just like with a C assert, the golden rule is don't have a side effect. Now in C asserts, if you have a certain paradigm, you can do certain things, because the entire program will either have a C assert on all of them or none of them. That's not true of contracts. They're designed differently. Every single contract is independent of every single other contract check, and the power set of contract checks in a program, any of them, is a valid program and will do nothing if the program is correct. And if the program is incorrect, the more checks you have on, the more likely it is to catch the bug. It's that simple. Now, no matter how advanced you are, if you ever have a contract predicate that would, in and of itself, evaluating it, change the essential behavior, you have a bug. Doesn't matter how good you are. That is the definition of a bug, because you have a case where you've got something there and nobody's supposed to know in a correct program, and yet the behavior changes. Then we have to call Ghostbusters. Okay. So this is just something we mustn't do. All right. In C++29, we have the ability to do these kinds of things. And I'm going to show you what they are. Just take a quick look. Now watch this. This is an example of having something built in. We don't have the syntax yet, but this is something that's coming. This gives us the ability to call these only when we're in some special high checking mode. This is a capture. This is one of the ways that when we do post conditions, we'll be able to say, oh, I want that value, and it's okay to change the parameter, but I've got the value. But that's something that the person does. And then finally, we have this ability that we're talking about. And again, these are just a few things to look forward to. So the language is not stagnant. Now, here's an interesting one. Implicit precondition checks, as in integer overflow, null pointer dereference, these kinds of things. Or how about just a plain old C-style array and you access it out of bounds? All of these things, right, can be checked at runtime implicitly if you ask. Signed integer overflow checks, as I said, this kind of thing, null pointer checks. So these kinds of things. All of these can be done today. We don't need to add this to the standard. So because of this, A compliant compiler today could just do all of this and it would be fine. Now, would there be overhead associated with it? Yes, which means that we leave it to compiler vendors to offer this in whatever way they want. In 29, there'll be a slightly more standard way to do it, but still they'll do it the way they want. And there's something even after that that makes it yet more standard, but it's a process. So in C++, by C++ 32, it'll look like there's an environment in C++, this is my projection, where you set certain standard environment variables as opposed to using the -d option, and you get the behavior you want, and all compilers refer to those dedicated environment variables. And they're not in the operating system environment. They're like const expr in C++. So this is a little bit, metaprogramming crazy, but it's really easy to use. Just because we use things that are really hard to understand how to write in the language doesn't mean we ever take that out on our users. So contracts are ridiculously easy to use, especially if you're doing straightforward, regular things. Then the more crazy you get, the more you can dig up more syntax to help you out. So I just want to make sure that we understand that it's not that hard. It's not hard at all. Has anybody heard? I guess you've heard about erroneous behavior, right? Did Timur talk about that? I can't remember if he did. No? All right. Erroneous behavior is an important other way to deal with stuff. So what is it? So we're defining undefined behavior to guard against security vulnerabilities when contract violations are not enforced. We did this once already with automatic variables that are referenced without being initialized. And this is important, and I need to explain this. Even though it's defined, it's still erroneous. It's guarded by a theoretical precondition that may not be checkable. That's the example of this, which we'll see shortly, is precisely the uninitialized memory read. What's important, though, incorrect use remains observably incorrect. It doesn't become correct to do it. It simply means that you can't optimize based on a bug. Okay, and that's good. You don't want to optimize based on a bug because that's dumb. You want to optimize based on things that aren't bugs, but you don't want to optimize on things that are bugs. Okay, so uninitialized reads, what is that? Reading an uninitialized automatic variable. This prevents, what we're doing is we're saying that the variable will now be initialized with some value. We're not going to tell you what value, but some value, but it's not indeterminate. That's all you get, which means you can't leak memory across things. So for example, here's an int, it's uninitialized. Now, if I do this, that's an error. It might trap because you might have a check here because you can know for sure in this local space, but it could be just an unspecified value. That would work too. So depending on whether you have active checking going on, it could catch it. This one, however, is most likely going to be just some value because this is beyond what we're able to check locally. We don't have the function body of G. Okay, so you get the idea. Basically, what we're doing is we're preemptively stopping a security violation. Okay, so we look at this, array bounds error, erroneous behavior, uninitialized memory reads. Can somebody think of something that's both? Hint, Rust has it, almost. So let me this one, signed integer overflow. We can state in C++ that signed integer overflow returns a value, not an indeterminate value, but a value, right? We can do that. But it also, like Rust, if you're checking, it can call the error handler. So if you have signed integer overflow and you're willing to pay for the checking, you'll call the violation handler, it'll log a message, and then it'll either terminate the program or continue at your behest. Does that make sense? So this is kind of cool, right? We see that we've got two tools now, and we have real use cases. I think that's pretty cool. Unfortunately, it's a harder problem than we'd like to admit. So we have to keep going. So you see where this talk is going? We're going to build up tools for safety. and we're going to put them all together, and we're going to conquer this beast. Okay, symbolic contract assertions. What is that? So imagine you have this. You can see that this is bad, right? We're calling a function on a supposedly a contiguous range, but there are two separate allocated entities there. So we see this as bad, right? What is this guy? All this does is say, hey, I'm telling the compiler or whatever external static analyzer we have that this is a fact. These have to be reachable. Now, this problem is not solvable in general with this technique, but it is solvable to an extent. So putting this on, depending how robustly your compiler wants to investigate, it has the opportunity to say, no, this is a bug. At the very least, it could warn. At the very least. So you get the idea. This can be done with local static analysis. So this whole idea of neighborhoods, very powerful. It can't do it. You can't check this by running code. All this is basically a label that says, hey, compiler. And by the way, every single precondition, postcondition, or assertion is also a symbolic check in that if it's not running, the compiler is still allowed to look at it and assume it's true statically. You see what I'm saying? In other words, it's a statement by the programmer that this is true. And if the compiler can observe that it's not true, even without running checks, it should probably warn. Anyway, so here's a standard container example. This happens a lot, by the way. So it's only a symbolic declaration, but you see these guys? It's called a compile time via local static analysis. So that's good, right? This is a harder example. So we have A. We now make A a little bigger. What happened? So we got A, and then we push back, and now what happens? It might change the internal buffer and therefore invalidate the iterators. Now we allocate B, and we do this very bad thing because it's possible that A doesn't refer to this to begin anymore, right? Do you see that? Does that make sense? So we put this thing in, and this is a symbolic declaration. And look at that. That's the problem. So it's a defect, but hard to catch via compilation time static analysis. So we can't use this technique for that. Okay, profiles. Disallowing, this is an example of where we could use a profile, perhaps. So here we have a proposed syntax to say that in this either file or translation unit, still to be determined, I'm in favor of file, profiles subset the language. What does that mean? Means that in this file, you can't use all of ISO C++. You can use a subset. Maybe it's a very large subset, but there's some things you can't use. And so here, we would like to say, this is bad. This is bad 100% of the time, right? This is not something you want to do. You don't want to cast something so that the bit pattern, literally the bit pattern, is interpreted differently, because that's UB just the same as if you had a union and you tried to do it with a union that way, right? This is just not kosher C++. But there are many other examples. Imagine if the unsigned had been a double. That might make it easier for you to see how bad it is, right? So this is something that we need to really stress. Profiles don't do anything. They simply rubber stamp that it's been done. That's a very important thing to get across. Profiles are not a means of doing anything. A profile is something that we all have a shared understanding. If you have something like a safety profile and it's well understood, then everybody agrees. If I see that stamp, that rubber stamp from the government that says, "Shh," then you know that all of these things are happening. And that makes sense. But we don't need profiles controlling anything. We need them establishing that they are done, no matter who does them. So again, this is my interpretation of profiles. It is other people's interpretation of profiles, but it's not everybody's interpretation of profiles. And so I encourage everybody to understand that we certainly want to take advantage of profiles to the extent that they make sense for everybody to communicate, and possibly even look into something that Vittorio Romeo brought up a long time, which is, what are they called? Epochs. Epochs. And I think this is a means and a way of possibly doing that. All right, moving forward. Exclusively enforced at compile time. This is what Rust does, and this is what Sean Baxter tried very hard to do to C++. So let's take a look at what that is. This is the law of exclusivity, and I will try to read it. If a storage reference expression evaluates to a storage reference that is implemented by a variable, then the formal access duration of the access may not overlap the formal access duration of any other access to the same variable unless both accesses are reads. In other words, multiple readers or a single writer, right? That's all that says. But that's the idea. That's what we're trying to do. So exclusivity during iteration. This is from Sean Baxter's paper. So we have int, and a vector, and now here's a for loop in there. And we've got this thing that sometimes does something. And we put this mute thing in here, which says that we need to have a mutable operation, and this cannot acquire a mutable reference during iteration, right? That's just not allowed. So we think maybe we'll fix it with this reserve. Now, certainly there's room. We can't possibly have a problem, right? And yet, nope, that's not how it works. The compiler has to make the decision on the code irrespective of any runtime aspects. So I want you to look at this. The only way to make this work is to have an entirely new standard library. That means incompatible with everything we do. And most people find that untenable. Now, it could be if your choice were either move to Rust or Swift, or have a separate standard library that you use for highly threaded code, you might make that trade-off. You might say, well, for new development, I'm going to do this, but for all my old code that I might need to add a little bit more threading, I might opt for this. It's a tool. It probably is not going to make it into the standard because it's too creepy for a lot of old C++ users. But it is a tool, so we're going to at least pay attention to it because it does work. Sean Baxter has demonstrated it very powerfully to many people, impressed many people. It's just that some people just feel it's not C++. All right. So exclusivity enforced at runtime. This is the cool topic. This is something that Lisa Lippincott has been exploring, and it's very exciting, and it might possibly be, very likely is, an answer that people can get behind once they get over their fear of ghosts. So, ghost data. Additional information made available to multiple contract assertions at various granularities, e.g., all assertions within a particular function invocation that would not otherwise be represented in the abstract machine. Anyway, this is not Lisa's description. This is Josh Burns and my description and Mongo's approval. So this is what we think it is, but it could be anything. But this is an idea. So I hope with this very deliberately vague explanation, some of this will make sense. Why do you think we call it ghost data? It doesn't appear in the code, and it might not be there. Excellent. So exclusivity during iteration. So here we go. I'm going to go through this and see what we got. This should look familiar. Ghost data tracks iterator validity. Does this look familiar with Sean's example? Do a vector pushback. Runtime check remains because vec might be allocated, even though it has the reserve. Notice that we're using the original standard library. I can't tell you how important that is. I just did. That's huge. The interoperability is there. What are we giving up? Compile time checking. What are we getting? We can write C++ code exactly the way we did before, possibly with a few extra annotations, but the point is it's still exactly C++ and you can use any algorithm you want. Seems good to me. At least worth investigating, right? So, iterator invalidation, include vector. Here we go. So, inherently not compile time checkable. We see this, right? This is not checkable. And again, we're using the same standard library. I just want to point out that this gives you a larger set of things we can do. Now, notice that what I've done here is I've added a precondition, plain old standard contract library precondition. Now, the precondition guards the UB. So there was UB in this, but now that I have a library precondition, all I have to do is turn on checking, and we can't get UB. This gives us the same thing in our own code that we can do automatically in the C++ standard language. Okay. This can't invalidate A anymore, and A can't be invalid. So this is what contracts do for us. They take away UB because the precondition guards it. So if the precondition isn't satisfied, you won't get here. I can't say it enough. It's like, this is the answer to how we make C++ safe. We combine things, okay? So let's put this out. With ghost data, assertions can express any requirement whose violation could alter program behavior. It's a good deal. Many assertions will require core language interfaces to update it. Okay. Ghost data has no runtime overhead when contract assertion checks are disabled. That's good. Rust doesn't give you that, right? Rust checks all the time, which is good for some people, but if you want that last ounce of performance, remember, you can have contract checks on all during testing and for the first year of production, or you can have a canary build where you have 1,000 machines running without the checking and 4 machines running with the checking. And if anything goes wrong, those canary machines report it back to engineering, and engineering fixes it on the next release. We have a release every week. So if we find a bug in a canary machine in the next release, it won't be there. That makes sense. Okay, so this is good. And local analysis can provide, can prove that the assertions will not be violated. Now, this is kind of magical. In an ideal world, if we could express everything, I don't know if anybody here's written compilers. I did a lot in school, but if you've got something like a production rule on the stack and you fill all the things, you reduce it to something, it's kind of the same thing with ghost data. You have a lot of ghost data potentially going on the stack, but if at compile time you can prove that things are okay, that goes away because you know the preconditions were met. So this is extremely exciting. We don't know how awesome it's going to be, but we know it's going to happen a lot, and that's really good. So, current safety project profiles. So I want to explain a little bit about how this works. 65% of the problem would be solved if we just did vector bracket. That would be amazing. But there's also another 20% that we could probably solve with just general contract violations. So then there's erroneous behavior. And then there's this other stuff. What's this other stuff? So lifetime issues. Lifetime issues in C++ aren't as bad as they are in C. You can handle lifetime issues if you work on it. You can use the right containers, you can do stuff. We have RAII. There's nothing we can do about data races in C++ today except use our heads and use appropriate tools. There are certain kinds of time travel debugging tools that might be represented at conferences that you might want to look at. And those are very effective at tracking down the really hard ones. And even Rust can't deal with these. And those same very fancy tools that you use externally and need to be proactive about can handle the rest, pretty much. So this is the landscape that we have. We cannot get 100% safety in any language. We can't, but we can come very close. We can certainly come a lot closer. So interaction of various techniques. Remember this? Well, we have a little bit more. We have symbolic contract checking. We have profiles. Oh, we have unallocated memory. We have data races. Look at this. Oh, wait. This is good. So I hope that's encouraging. How am I doing on time? Oh, I'm halfway through. All right. Other project priorities. I don't want to dwell on this. We're doing this. So I'm just going to show you what we're doing. Because if C++ doesn't have the ecosystem to do what it needs to do, then people aren't going to use it, even if it has really good stuff, right? So we need to do this stuff. We want to use GCD and Clang to do this kind of work. So anyway, that's all I wanted to say about the ecosystem. We are working actively to make sure that we fix bugs in GCC and Clang, that we make sure that features that we need are added, important features. We're not going to do everything because, we need help. I mean, anybody who's interested in helping us, as I said, you know where to find me. I'd love to work with you. And particularly if you go back to your companies and say, it's in our best interest. We use a lot of C++ here. And it would really make sense if we all pulled together and actually started contributing to it. C++ is by no means going away. It's never going away. The world runs on C++. So it's going to be here. The question is, do we want it to be here and be a legacy language that makes people feel punished to work on it? Or do we want to keep it vibrant and alive, because it is something that a lot of major companies depend on. So some people don't like allocators, but I'm just going to tell you that there's some good things going here. They were invented by me in 1998 at Bear Stearns, brought to Bloomberg in 2002, and we have all kinds of successes with the standard in 11. We got in a flavor of it. In 17, we have the same kind of allocators. We use the polymorphic allocators. We have a book coming out by Josh Byrne on C++ allocators for the working programmer, and it'll walk you through how you take long-running code and restore its performance as if it had just started. So you don't have to reboot your machine every so often because your memory has become diffused. And that'll all be explained there. More standard library support is something that Bloomberg is advocating. And by the way, if anybody's interested in understanding allocators, my 2017 meeting C++ talk, there's 2 parts, is probably at least a best talk I've ever given, all modesty aside. And there's a lot of information there. So again, meeting C++ 2017, local arena memory allocators, I would recommend. And this is really cool. This is like the next generation. We would like allocators to be in the language so that they are more applicable and less work to plumb in library code. In other words, we want them to be able, if you create a struct, it should just work. And if you want to add an allocator to a struct, you don't have to add constructors and all this stuff. It works with a back channel. And that's another topic. Efficient trivial relocation. We got this into the standard in February along with the contracts. So that was very, very pleasant. And it does some good things, and I just want to put them up while I take a drink. I'll let you read. Save my voice for something useful. How many people know about trivial relocation? How many people have never heard the thought of it before? Okay. So just in a nutshell, trivial relocation is allowing, is labeling a structure to say, compiler, I am okay if you use mem move. You don't need to use no stinking whatever. And afterwards, you just let it go away. Don't worry about it. No destructors or whatever. Some things are really good like that, but you have to tell the compiler it's okay. And if the compiler agrees with you, then it'll do it. So this is an example, and this implies that it's a candidate for bitwise relocation. And here's main, and here's a vector, and here's a loop. Okay? And these are the things that we would like not to call. And so they won't be called because of that label. And we just save all kinds of calls that we don't need to do. So this is a performance improvement. It's also a step towards exclusivity. It was kind of cool. These are things that give us some advantages, some safety advantage. So compile time reflection adds a lot of possibilities, and these are some things that we might be able to do. The mix-in one scares me. Mix-in gets to look at whatever is using it and do funny things, and I'm like, whoa, okay. Anyway, so current project priorities. So contracts. So the C stands for correctness, the S stands for security on the bottom, the H stands for health of the environment, the M stands for the machine efficiency, and the H stands for the human efficiency. And so if you look at contracts, you'll see that the black box means that's what it's doing. And the yellow box with the S in it is saying, well, it touches on that too. Okay, so there's some security aspects with contracts, but it's dead focused on correctness. Now, if you look at erroneous behavior, it's the other way around. Erroneous behavior is dead focused on security. It doesn't do really much for correctness, but it's kind of overlaps it a little bit, so we put it like that. Then we have memory safety, and that's dead aimed at both. So the memory safety that I put there, what we really mean by that is the techniques that are in the last two categories, either the, because memory safety, really the lifetime one is what distinguishes languages like Java from Swift, and the race conditions especially. So that's that. Then we have, okay, so bug fixes and maintenance. I think it's pretty clear that if we don't have bugs, then the security goes up. That's probably pretty reasonable, but it's mostly about improving the environment. And then here, this is really just about making it more efficient for users. And then here we have, this is allocators. Having trouble seeing this. Allocators and trivial relocation, and you get the idea. Trivial relocation, a little bit about correctness, but mostly about machine efficiency. And then reflection, here we are, is all about human efficiency. So summary and conclusion. And by the way, I have some bonus material. Don't panic. In the event that we run out of questions, which is kind of cool, but we need C++. C++ needs us. We hear you. to C++. Somebody should do something. We are. North Star. Make C++ such that we can and want to use it 25 years from now. Not 5 years from now, not 10. Why? And by the way, this is ongoing. The North Star is not something you can ever reach. It's guiding us. So that's what we mean by the North Star. If it doesn't help us in 2 years, that's not a reason for us not to pursue it. Because if we are looking long term and we keep our eye on this ball, then eventually we will get to a steady state where the work it takes to keep correcting it is minimal. That's the goal. We have a long way to go right now, but we will have more to do. So our top level strategy, maximize the SHE in C++, which is safety, health, and efficiency. We have this nice acronym that I use all the time so that I can remember what those three things are in what order. And it's just very fortunate that it comes out to something that is a nice word. Making C++ safer. Contracts, erroneous behavior, memory safety. Making C++ healthier. Bug fixes, C++ 26 conformance. Making C++ more efficient, allocators for the machine, trivial relocation, and relocation, and then reflection for the human. And this is the C++ safety roadmap. So this is stuff that we plan to do in 2025. So of course, we're going to maintain C++ in Clang and implement new language features in GCC and Clang. Then we're going to follow up on the minimum viable product per Sean Edwards, who's the CTO, Bloomberg, my boss's boss's boss, and control of evaluation semantics. Now, this is a big one. The file-based control of evaluation semantics is going to be a way that we can portably pass around what we're trying to do in different build configurations. So that's going to be very helpful in practice. Having a common ABI across GCC and Clang is a goal. Okay, in allocators, the side channel project is something that we're starting to work on. Allocators, test memory resource for allocators, something so that we can do testing. Obviously, that's safety related as well. Contract assertions on virtual functions. Sadly, in order to get the contracts MVP in, we got it all the way in. It's kind of like a mini repeat of C++20. We got it all the way to core and it was all good with virtual functions covered. And then some people got cold feet thinking, maybe we want to go back to the 1980s and you do what Bertrand Meyer did, which was a very good rule of thumb, but is mathematically wrong. And so not general enough to do what we need to do in C++. For example, in Bertrand Meyer's world, you have a hierarchy, and he used the expression, you have wider preconditions and narrower postconditions. Well, that doesn't make sense if you have a base class function that works on only non-negative numbers, and you have a derived class function that works on all numbers. Then it's entirely possible that when you pass in a negative number, you'll get a postcondition that's outside of the range that was allowed for the non-negative numbers because you have more inputs. And so it could be that all negative numbers are in the billions and all positive numbers are between 0 and 5. So it's completely reasonable that a derived class, like you have a car and then you have a race car, well, a race car can go 10 times faster than this car, 2 times fast, 3 times faster. So none of that applies and none of that makes sense. Moreover, there are cases that the static hierarchy isn't true the entire life of the program. Very classic example with the car cases. Imagine you have a bunch of car types. One of the car types is an electric car. The electric car, when the program wakes up, is not charged, so you need to charge it. Then it does what it says it's going to do, but at the beginning of the program, it doesn't. So it violates the static contract. So we don't have static contracts. We have runtime checking. That's okay. Why would I mention the electric car and charging? Imagine the same thing where you have a database connection, and when it wakes up, the database isn't connected. So you need to connect it. Imagine a situation where the thing doesn't work until you start threads. We have to start threads, so it's not working before the threads. My point is that object-oriented hierarchies that are static are fiction, and there's a generalization of it that says it needs to be true when the function is called, not throughout the life of the program. So some people panicked, and so that got taken out. It'll go back in exactly the same way as it went in once we've implemented the other way and show them that it doesn't work. But we are implementing the other way because we're a we're an inclusive society. We want to implement bad designs for other people to see how bad they are. No kidding. Sometimes that's what it takes. Contract post-condition captures. I told you about that. This is something that's coming. We need that. Requires clause for contracts. Labels. This is huge. Remember when you saw those audit and the other things? Those labels will allow us to control the semantics of a particular assertion and identify it. So we can control that using outside means. We don't have to go in and change the code. We can just identify it. Or we can say, regardless of what's going on outside, I want this enforced. And that would very often be used in a test driver because you want to be able to do different semantics and see that they're all working the way you want in a single file. So we need that feature. And factored API for calling contract violation handler. Okay, so if you want to roll your own macro-based thing, but if something goes wrong, you want to call the handler, you should be able to do that because that's a piece part of this system. And C++ is an open system. So if you want to get at a very clean interface to something that does something very well defined, that's awesome. This is also hierarchical reuse. This is something I'm very proud of. This is what I taught forever. In large-scale designs, you want to have all of your piece parts available. So when you build your first subsystem and then you go, it's time to move on to the next subsystem, you don't copy paste the subsystem over and start tweaking it. You take the piece parts, which didn't change, and you add a little bit of code and you call it a day in 1/8 the time that it would have taken you to do it the other way. And this is how we roll. All right. I'm not going to do the same thing I did before and tell you what we've planned for the next 10 years. I'm going to take a drink of coffee and let you take a look. And people at home can look at it. But this is an idea of the kinds of things that we've got planned for 26. Is anything in here? Does anybody see anything in here that interests them or thinks that shouldn't be there? Any thoughts? This is mostly just a picture of what we're trying to do. Oh, sorry. I'll go back.
I was missing the hardening proposal.
The what?
Precondition hardening.
Precondition hardening. Okay, let me talk about precondition hardening. That is what we're trying to do with putting contracts in the core language, because that is the same thing. And precondition hardening is something that there's a white paper for it, and it's happening. In other words, the white paper is going on, and once all of the UB is identified in the language, then it will be our job to assign a technique for finding it and guarding it. Does that make sense? So we're doing that. We don't spell it out. The closest thing we have is assertions in the language. And as I said, we can do that anytime because we don't have to change anything in the standard, because every piece of UB that we're trying to fix is undefined behavior. So it can do whatever we want. So if in a particular, let's say GCC and client decide they want to have a switch that says hardening, they put the switch in and it's hardened. Then if you want to have a profile that says hardened, put the profile in, then it won't compile unless it's hardened. So that's how you compose these things, the piece parts, to get what you want. Does that make sense? Are you totally happy or just mostly happy? Oh, totally happy. Yes. All right. I just want to make sure I'm not going too fast. So here's what we've got planned out for.
So John, before you continue, I just wanted to clarify something with you. When you say we're planning this, we're doing that, is that the work that Bloomberg is funding? Is that what when you say we, or is it a wider consortium that you've put together?
So yes. Hold on just a second. This is very annoying. Stop. Okay. Technology is killing me. All right. Stop. Apologies. Yes. So the question was, is this Bloomberg that's doing this, or is this the greater consortium of people? The answer is yes to both. This is what Bloomberg is doing. We want help because this is a lot of work. It's all good work. There's no trouble. It's like good work. But it's not fair or practical that Bloomberg does it all. Plus, different people will have different focuses on what they need. So it would really be great if we worked together, divvied up the work, and if you have some particular interest, great. And you have, say we have some expertise in something you're interested in, and you have some expertise in something we're interested in, we could possibly not have tariffs and just trade knowledge, just do it like normal people. All right, sorry. I try to keep this sterile, but I can't. Next one. And again, I'm just showing this to be, just letting you know what we have in mind. This is not, and I really do mean, we don't know exactly what's going to happen in the long term, but these are some of the things that we haven't sorted out yet. But just to give you an idea, these are all things that we know it'd be nice to have if we had the resources to do it, but we don't really have the resources to do all this. So we have to take our time. And even though management is being very generous with us to do this and very supportive, there are limits even for, multi-billion-dollar companies. They still have to do their everyday work, but they have the foresight, and this is important, they have the foresight to know that they're going to need C++ 5 years from now. And that if they don't do something now, and nobody does anything now, it's not going to get better. So, importantly, the best way to predict the future is to create it. So, we are. Join us. That's my email. Anybody would like to help us, work with us, anything, if you have any questions, you can reach me there. So, I'm going to pause here because we have actually got some more time, right? We've got about 18 minutes. Does anybody have any general questions?
So regarding ghost data in 26, what form would that take exactly?
Okay, ghost data in 26, not happening, not close.
Okay, that was in a slide, that's why I asked.
Oh, working on it.
Right.
Oh, we're researching it.
Oh, okay.
My apologies. Ghost data will not be in 26. It likely won't be in 29. We're really hoping for a general answer in 32. But I think we'll have an answer by 29, which means that 3 years from now or 2 years from now, whatever, we might be able to tell the world in a proposal to the Standards Committee, or at least in a white paper that says, here's what we're going to do. That's going to require research. It's going to require prototyping. It's going to require time. But the payoff is enormous because if we have this is a superset of what the other languages can do. Swift is kind of like a little bit ghost data-ish, but we want to go full on. And so, as I said, this is a research topic. I'd love to have other people who are very knowledgeable, interested in this kind of work to reach out to me. Lisa Lippincott is, second to none at a combination of mathematics, C++, and user interfaces. That is what she does, and she does it really well. And her solution to putting contracts on pointers is genius. She said she's going to put contracts into the type system. I almost had an aneurysm. And then she said, but you'll like it. And I'm like, okay. And then I listened and I did. It is really genius. She was teasing me when she said, she did put it in the type system. Literally, the words are true. But you wouldn't know it. You'd have to, no, you wouldn't notice. So, any other questions? Okay.
So I've got one very specific question and then a slightly more general question. So does the library hardening that's I think coming in C++26, I wasn't quite clear. Is that opt-in or opt-out? Like if I just compile GCC foo.cpp, do I get library do I get the library hardening?
You're asking a very good question. I am not the best person to answer that because library hardening is going to use contracts. Okay? So there's a layering issue there. And contracts are controlled by the vendor, right? And what the default is, I would love to have all contract checks on everything by default. Because if you don't know that you need it to be faster, you definitely know you need it to be safer, right? If you don't know it, right? So there's a natural consequence that first find the bugs, then make it fast. Nobody I know develops software in optimized mode. Does anybody?
I mean, I think a lot of people do, but they maybe shouldn't.
Well, think about it. I mean, why would you do that? It takes longer to compile. Yeah. So my point is, compile in unoptimized mode and then optimize. If somebody wants to be so weird as to say, we're going to tie the two together, so as soon as you get above 01, we're going to turn off all runtime checks, that's your business. I wouldn't do that. What I would do is keep them separate. We often run in optimized mode and still have contract checks on. That should be okay. But it shouldn't be too hard to do that. The default should be safety first. But never give up 1 microsecond, maybe a nanosecond. But you know what I'm saying? Don't give up the performance advantage that C++ is number one on, because that is its bread and butter. That is what makes C++. Don't allow another, I'm going to use the word a boutique language with a special feature. I'm not talking about Rust. I'm talking about anything that has a capacity, a capability that C++ doesn't have, that would allow that thing to squeeze its way in and get a hold. Make sure that C++ can do everything that is needed by a super high performance systems multi-threaded enterprise level language. That's what we want.
And if I'm indulged with a slightly more general thing on the runtime checks, which sounds super interesting. And just how do you view that in compared to say like sanitizers, which are sort of compiler features doing more heavyweight runtime checking?
Okay, so the question is, what is the difference between literally precondition and also postcondition checking, those kinds of checks, and sanitizers? Contract checking is done by the developer. It's precise. It turns the plain language contract in the component that you're talking about, the function, into something that can be partially checked. The plain language contract is boss. And then you put something in that says, if this thing is called, this must be true. And that is a human being do it. It's not a machine.
And is that the case for Lisa Lippincott's work as well? Is
it what?
Lisa Lippincott's work that you referred to?
Lisa Lippincott's work, well, yes, you'll have to specify things,
right?
But the point is, the things that you specify will be much more expressive than they are today. You'll be able to deal, for example, the goal is ultimately somebody passes you a pointer. You don't know how big it is. You just have a pointer. Okay. But then you add 5 to it and dereference it. What? Right? The ghost data will provide the information to say, And that's what's important. Does that make sense?
Yeah, thank you.
So a point that Sean Baxter makes a lot, and I think is a good one, is that some of these kinds of experiments are in some ways better if we go ahead and land them non-portably in certain implementations, learn to use them at least when it's appropriate, and then you also use that to inform our designs and stuff. Is that part of the plan that we might see, let's say a __GCC_ trivially relocatable if something like, and then we could guard that with macro that we can compile in and out in different platforms and that sort of thing. Is that part of the plan that we can release that earlier rather than wait for the full cycle of ISO for people that can early adopt and can use GCC 17 next year and things like that?
Okay, so we did have a slide that was supposed to address that. If you remember the waterfall-like slides with all the arrows where it comes down and eventually gets to production. So I think your question is, when we're designing a feature, you saw that bzzz, where we're going between, that is the prototyping phase. So yes, during the development of the feature, there will be prototyping and feedback and prototyping and feedback. And that local thread, which isn't part of trunk, it isn't shipped with everything.
That's what I was getting at.
Yeah, but that certainly could be made available for use. So the answer, I think, is yes. But I don't, it's not like we have a planned date to do something. It's just available. Like if you want to pick up where we are and try it, sure.
Right. So it may, so it sounds like if it makes sense for that feature, then it could land in main and trunk as a compiler extension or something like that.
Of course.
And then people could use it with a macro so it's portable or something.
We did that with C++20 contracts.
Right. Okay.
We have, no, so we absolutely can do that. And again, what I'd really like to have is the ability, as soon as as soon as the feature freeze on the contract, on the compiler is done, I'd love to get that code, which might be buggy in the compiler, so I can debug my code at Bloomberg, not me personally, so that when the thing finally, the productized compiler is shipped and C++26 drops, we can immediately turn on C++26 in theory.
Yeah, that sounds great. Because what you said about canary builds and certain machines running certain versions of things, like it has to kind of be in a mainline compiler for that to even be viable for some of these features.
Okay, so the canary builds had nothing to do with trying to move to a different thing. That's when we're working on code at Bloomberg. When we're working on code at Bloomberg and we do something, we might have contracts enabled in only 4 of 1,000 machines because we want to know if our own code is buggy.
No, but other people might want to use the same technique, but they use a different container that includes. Anyway, the point is, like, if the only compiler you can use for, like, for example, for a current static reflection, like compile time reflection, basically the only compiler you're really going to use is the compiler explorer compiler, and you're not really shipping anything out of that, right? So if it lands in main trunk or whatever of the relevant compiler, and like people can use it if they want to, it's maybe a little dangerous, but that's what canary things are for, right?
Yeah. Well, sure. No, really, the canary things are for. If you have checking on everything and you want to improve your productivity, you don't have checking on everything. You have checking on a few things. And that means you get more throughput. That's all. Anything else? Tell you what, I'm going to race through the last few slides because they're cool. And anybody wants to leave, it's fine. I'm going to just tell you that this was the sorest spot of contracts, but I just have to run through it. It's not even it should take like 5 minutes, I hope. So if you're up for it, if you want to leave, that's fine. You won't miss anything on the safety, whatever, but you will learn about what constification is, if you care. So, or not, because it's not letting me go here. So constification. The idea here is that when you have a predicate, the last thing you want to do is have a side effect. And so what constification does is it says that every named entity in your predicate will be treated as if it were const. That means were you to have, for example, an overloaded function that did 2 very different things, you would get a different result. That would be very bad. The good news we'll find out is that never happens in practice, and there are reasons for that. So this is an example here where the function might modify the argument. And we don't want that. We really don't want that. So what'll happen is this will not compile. Oh, and I left that thing at the bottom, which I didn't mean to do. Oh, well. So this is bad. Or maybe I did. Oh, I'm sorry. I take it back. Ignore what I just said. I did want to leave it at the bottom. So this is keeping it constant. What we're basically saying is we want to make sure that we don't accidentally change what we're doing. We have to do it very deliberately. That's the point. And so this is a const correctness bug, and we need to fix it. So we fix it. And here we have an example of a map where we really need to do something else. So we have this thing called unconst, where we say if the thing is doing the right thing and we know it's doing the right thing, then we can go ahead and say, yes, it's okay, and call it out. Now I'm going to go over all of this again, one by one, a little slower. So here's some data. We looked at a lot of code bases and we say, constifying what's in the predicate. How often does that change things? And does it ever change things for the worse? So let's take a look. 99.03% of the time, there's no difference. That's good, right? There's no difference, 99%. Then there's this 0.8% where the overload resolution changes. So you go, for example, from a modifiable iterator to a const iterator. I hope everybody knows that the difference between a modifiable iterator and a const iterator is that a modifiable iterator is a const iterator that's modifiable, that allows you modifiable access to the element, and that's it. If it did anything else, it would violate Liskov substitutability because that's the design. If it were to violate that, and by the way, I do mean Liskov substitutability, not what other people talk about with virtual functions and nonsense like that. Talking about literally the subclass does everything the same way, the superclass does everything the same way as the subclass when the function is called with the data that is able to be passed to the subclass. That just has to be. So it turns out that this happens 8% of the time, and here's an example of that. Oh, that was a little quick. Here's an example of that, and that's perfectly fine. We've got the iterator and the const iterator. Begin and end and the const iterator, and this just works. All right, next one. Then we have these guys, and if you look at this, fixed const correctness bug. So if you have a const correctness bug, like here, and it constifies it, that won't compile. But the bug is detected because of constification. So this is a pure compile time win. Pure compile time win. Nothing, but if you don't want to change it, you can const cast it away. You can, but the right thing to do is to change it. But if you can't change it, you can flag it as being a bug, not just have it not be visible. So that's good. Now let's look at destructive checks found. So here we have this, and you notice this is a destructive thing. This will actually add elements. So this is a bug in the user. And so the bug is detected by constification. That's a pure win. That's awesome. Then we have this very, very rare case where you're using a function that isn't const because sometimes it modifies it, but in this case, it doesn't modify it. In Ghost code, where you never want to modify anything, and certainly not destructively, this is very rare. But it does happen. So here's an example where it happens. What do? We do that. And it's fine. But you've now made it clear, you've looked at it and you've said, yes, this is a special case. And it's really ugly, long and nasty, and it shows up. We could make that much easier by using some meta stuff and just having a macro called unconst, and then you just say unconst to them. And that would be very descriptive and very short and very easy to do. And 3 times out of 10,000, you'd have to do it. How bad is that? Oh, then there's one last one. This one. You see that one there between the const cast and the fixed const? Do you see that one? This is the case where you write some nasty code where the const changes the meaning and it actually does something completely different. So this doesn't happen. It can't happen. Because if it did happen, nobody could use it. If you overload unconst and non-const in any program, as soon as you pass something by const reference and it does something different than it did if you passed it by, or if you just used it on the program stack, which is what happened, all heck will break loose. I actually did this once. If you do that, I had a database, and if you, I wanted it to be, if you asked for something from the database and the reference was const, it would give you a const null. And if you asked for it, or value, if it was there, otherwise it would be null. And if you asked for it with a modifiable one, it would insert it and give it to you. I was very young. I did it once. I went home the next day. It was in production. They called me up and they said the database exploded because they iterated over it with a modifiable variable. And it was death. So it's kind of like petting a lion. You do it once and you learn never, ever, ever do that again. So that's what I did. And this is definitely bad because it's not a viable overload. I did this. I regret it. Never again. So this doesn't work. It doesn't happen in practice. But if it did, Constification would take the mutating bad thing and turn it into a no-op. A no-op. At worst, it's a no-op. So this at least doesn't make things worse in the 0.00000% of the time that it happens. And finally, if anybody writes code like this, they should be spoken to harshly. This is not viable. This is the opposite of Liskov substitutability. That's called stupidity. This is just not reasonable in any world. And basically, that's my comment. So I think, did I just run out of time? I expect I did. Yep, okay. Thank you again for coming, and that's it.